Okay, so nonlinear equations. The problem generically in nonlinear equations is that you have some function of n variables and n outputs. So you have, and you're trying to compute f of x equals 0. You're trying to find some x such as f of x equals 0. Now, by the way, that's what you're trying to solve for a 0 of f. Now, another kind of problem is solve for a fixed point of f. That is trying to find some x such that f of x equals x. Mathematically, there's no difference because the fixed point of f of x is a 0 of f of x minus x. It's just that sometimes you write it one way and sometimes the other. That's all nonlinear equations. Now, by the way, this is all done in Euclidean space, finite dimensional Euclidean space, but many of the ideas that we're using here that I'll be talking about are directly applicable to problems in Banach spaces, in functional spaces. And I try to present these things using basically the basic fundamental mathematical ideas that do generalize. Now, existence, I'm not going to talk about existence. There's Brouwer's fixed point theorem and Kakutani's fixed point theorem and a variety of fixed point theorems or theorems and zeros to deal with that. Now, by the way, there has often been in the past an obsession within mathematical economics with proving existence theorems for some equations. Now, by the way, that focus does not exist in physics. Physicists go ahead, write down a system of partial differential equations or whatever, and they don't really spend a lot of time on proving existence. And in particular, there are these prizes that are given. There's a list of, I think, 7 prizes. You solve 7 problems, and you solve one of them, you get $1 million. I think one of the recipients several years ago was the guy who solved Fermat's last theorem. And one of the problems is proving existence of particular kind of Navier-Stokes equation. Now, that may be disturbing to those of you who fly airplanes because Navier-Stokes equations are heavily used in anything involving aerodynamics. We don't have existence theorems for it. We don't have relevant existence theorems for that. You write down these Navier-Stokes equations. There does exist something that we call a generalized solution. That means that it's there is a generalized function that solves it. Well, generalized functions include things like direct delta functions, etc. There's no physical function. There's no proof that there always exists a physical solution. But that doesn't bother people. The same is true with uniqueness also. Physicists, they don't focus on uniqueness of solutions either. Now, I'm not saying that these are unimportant issues. They certainly are helpful if you can do it. But the attitude that I take is to proceed, but in a careful fashion. And again, going back to the concept of epsilon equilibrium, numerically, all we can ever compute is an epsilon equilibrium, something that comes close in some relevant sense to solving a system. And that's the goal here. And so if physicists do not wait for the mathematicians to prove existence theorems, and I don't think economists should wait either. It's a matter of proceeding, though, with care and with awareness of the underlying mathematical issues. Okay, now, examples of this are just all over economics. Arrow-Debreu general equilibrium theory, find a price such that the excess demand function is 0. Nash equilibrium of games when you have continuous strategies. Or mixed strategies. Nash's fundamental paper finite strategies, but then he solved it for mixed strategies and using Kakutani's fixed point theorem. So there's all economics, when you talk about equilibrium, that is going to boil down to solving some system of equations in some topological space. Now, okay, let's start with the basics. Suppose you have one dimension. Well, one simple method is bisection. So suppose you have some function that you're trying to find a zero of that function, and suppose that you have a point A where you say, oh, f at A is negative, and then there's some other value B, oh, f of B is positive. Well, then by the intermediate value theorem, this is assuming, of course, that f is continuous, you know that there is a zero between A and B. And how do you find it? Well, you kind of think about a pack of dogs hunting a wolf, you know, like in those movies about England in the old days and the aristocracy. So you know that the zero is to the left of B, to the right of A. So then you jump to the midpoint, C, and say, okay, now is f positive or negative there? Oh, it's positive. Okay, now you know you've got it trapped between A and C, and you just keep dividing in half, and then you keep getting it trapped, and then you will converge to the solution. Now, by the way, in this case, suppose that this f of x actually went down here, and there were other solutions. Well, this method just would go by them. Bisection will find a solution. Certainly not all of them if there are multiple solutions, but it will find a solution. And by the way, I didn't mention it in the optimization, but in unconstrained optimization, there is a similar but kind of more of a headache to describe method to isolate the minimum, which basically, you see, minimizing f of x boils down to finding a point where f prime is equal to 0. So it boils down to finding solving a nonlinear equation. And so then there's an unconstrained optimization version of this also. Now, that's one-dimensional problems. Okay, there. Now, as you might expect, we are going to talk about Newton's method, but first, let's look at it in one dimension. So basically, what happens with Newton's method for equations is that... I think somebody has their microphone on who probably doesn't want to have their microphone on. Okay, so... so the idea here in Newton's method, very similar to Newton's method for optimization, is you have an f of x and you're trying to find a zero of f. So you're at some point, let's say this is your most current guess, you're at that point and you then replace f of x with its linear approximation, and then you solve for where that linear approximation has a zero. And in this case, you get this nice line goes down here, and then you iterate. Now, let's look at some video examples of this. So this is one of those CDF files that I posted. Now, suppose you're trying to find a zero of the cosine function between 0 and 2 pi. Now, if you start here, you see this black dot down here, you start here, then you go up to here. Well, it's close to being zero derivative, and then it goes flying off over here. And as you can see, it doesn't stay within the interval 0x. This is a cosine function, so you know there's multiple zeros, so it bounces off to some other zero. Now let's look what happened if we step forward and go to point 0.5. Well, now it goes up here, comes down, and then bounces around and does, converges nicely to that point. And then now as we increase the initial guess to 1, boy, that also is beautiful. Just notice that after you start at 1, but then very quickly converge to the nearby solution. And there you basically start at the solution. Here you start close, and here also you're nice. Now here what happens is that, again, the slope here is rather, it's a small negative number, so the 0 is over to the far left, and then it looks like it's converging to another 0 minus 4.7. Then here what happens is you start here at 3.5, you go down, you go over there, and then you're off to the left again, and apparently going to converge to some negative number. Now this is what we kind of like to see. We start at 4 and we end up going to the solution at 4.7. That's nice, sweet, all this is very nice. Oh, but what happened here? If we start at 6, then the tangent approximation puts you down here, and then you go down this point, you get a tangent approximation. You end up converging, but notice, you start over here at 6. The nearest solution is like at 4.7, but no, does Newton method go? No, it goes past the solution at 4.7 and converges to the one down here at roughly 1.6. So Newton's method with this linear approximation stuff does bounce around. And so now, when you see, notice that you might consider this 6 to be a good initial guess, and what you're aiming for is this solution. Or let's say that you think of this as an economic equilibrium problem, and now if you start at like back here, if we started at numbers down, numbers like, okay, where? Now, here we have big numbers, let's say, and then, okay, there are some cases where it would iterate and then converge to a negative root. Well, the thing is that if you're looking at an equilibrium, negative prices don't make sense. And so you may write down a problem, but the solution, but you write down in a mathematical form, which has nonsense solutions, such as negative prices. So Newton's method will jump around a lot. And we'll find ways of fixing this, but nonlinear equations are harder to fix than optimization problems. Because see, with optimization problems, let's say minimization, the whole objective is to go downhill. Just go downhill. Find a way to go downhill, and you know you're moving in the right direction. With nonlinear equations, you don't have any idea of what a good direction is to go. So it's a harder problem to deal with. Now, of course, we have the glorious quadratic convergence result also. So that's so if you start close enough, then it'll converge. So if you already kind of know the answer, it'll quadratically converge to a better answer. Now, sometimes Newton's method will just not work. Consider this function. F of x equals a cube root of x times e to the minus x squared. Now what happens is that this is going to blow up, go bad. Here's the function. Now, by the way, in Mathematica, if I did x to the 1/3 and x negative, then it would give me a complex value. So you have to do this sine of x, absolute value of x. I don't know in MATLAB what the convention there is, but this is for these languages or packages that allow taking fractional root of a negative number. You have to always be aware of whether or not it's giving you the real solution, real or root, or excuse me, a complex one. So this is the graph of the function that we're looking at. Now the solution we're looking for is here. Now, by the way, we're looking for 0. Now, by the way, there are two other solutions. Notice that if as x goes to infinity, this whole thing goes to 0. So there is a solution in some sense at minus infinity and at plus infinity. So on the extended real line, there are 3 solutions. So the pathology here is not going to be all that surprising when you think about that fact. Now, so then I compute the Newton iteration, and what happens is that basically, now the solution we're looking for is going to 0. Now, what you see is that no matter where you start, the next iterate is not going to be 0. And you go to 2 iterates, the next iterate isn't going to be 0 because these lines do not cross the horizontal axis. The only way that the next iterate is 0 is if you start at 0. And then here's 3 iterations. So unless you start at the solution, at x equals 0, then this is just going to blow up. But as I said, what's going to happen is that it diverges. You iterate this, the iterates diverge to minus infinity or plus infinity, which kind of are solutions, but not what you're looking for. So that's now why doesn't the theory apply? Well, it's because at this point, the Jacobian has infinite slope. So one of the key assumptions of the theorem for quadratic convergence is that the slope at the solution, as Jacobian in general, be well behaved. Now, the other possible pathology is that in this case, you converge to a cycle. You start here, you go up over here, you converge to a cycle, and that's not good. Now, when you're doing general equilibrium, there's something else that can go wrong. You might start thinking, well, so many things go wrong, what's the point of learning these things? But anyway, we'll fix them. So now suppose you have a demand function. By the way, this is an example taken from a paper written by Kehoe, the micro Kehoe. And so if you have this is basically a constant elasticity of demand curves. And there are 3 equilibria, one here at 0.5, 0.5, one down here, one down here. And so then I'm trying to find equilibrium basically where there are these 2 people. I equals, D super I sub j is Mr. I's demand for good j, I think, one way or the other anyway. So you end up with this function for the excess demand, this curve for the excess demand function. Now, if you start here using Newton's method, start here, take the slope, your next iterate is going to be a negative price. Well, you stick a negative price in here, and well, that's nonsense. You can't have negative prices. That's not going to work. I mean, it's going to blow up on you. So again, you have this issue about Newton's method may send you to regions where the demand functions or the functions you're trying to find the 0 of do not exist. So you have to be careful about this. Now, I'll get later to methods about how to be careful. Now, in some cases, f prime of x may be costly. Not likely for one-dimensional cases, but let's say, hypothetically, you don't want to compute directly the derivative f prime x. So in that case, what people do is use what's called the secant method. What happens is you approximate the secant, the f derivative at xk, with the secant of f between xk and xk minus 1. So that's just basically, you know the function xk minus 1, you know the function xk, you just take a straight line through that, and then that's your linear approximation now for at xk, and then you use that, and you get out your new guess xk plus 1. Now the secant method, if the derivative at the solution is well behaved and everything's continuous at the solution, then this will converge not at a quadratic rate, but at rate 1 plus 0.5 over 2, which is better than 1, better than linear. Maybe not a whole lot, but it's better than linear. And so you will get convergence with the secant method, but not the nice quadratic rate. So that those ideas from that are for one dimensions can be applied directly to solve multivariate problems. Now, and this is going to be the Gauss-Jacobi and Gauss-Seidel method. So suppose you have a function of n functions of n variables, and you want to find f of x equals 0. So you have f super 1. The first function, f1, is a function of n variables, etc., and down to the nth function. Now, the Gauss-Jacobi method for nonlinear equations is basically the same as it was for linear equations. You have your old guess xk. Now then, you want a new guess for x1. What you do is you take equation 1, you use the old guess for x2, x3, etc. up to xn, and then you now solve for x1 for where you find an x1 k plus 1 value to make that equation equal to 0. Now this is just a one-dimensional nonlinear equation. So this, you can just pull out bisection or whatever or something to solve that. And then how do you get x2? Well, then x2 is where you fix x1, x3, etc. at the old guess, and then you have only one variable that you don't know, and so you just solve that one-dimensional nonlinear equation for x2, and etc. for each of the x's. So now you have reduced the n-dimensional problem into n one-dimensional problems. Okay. Again, this is the same thing as with Gauss-Jacobi in general. The indices matter. You want to make, how you label things x1, x2, and how that labeling matches up with the f1s affect things. And so what you want to do here is you want to arrange things so that the Jacobian of this thing is close to being diagonal. And then, so basically, you want to label these equations and the variables so that x1 is the dominant unknown in the first equation, x2 is the dominant unknown in f2. This is like we talk about apple, banana, chocolate, tetanoma. If x1 is apples, then this should be the apple demand function, etc. Now, one last point is that this is parallelizable. If you have 1,000 equations and 1,000 cores, then you can just have the 1,000 cores do these 1,000 equations to get your next guess. So this is parallelizable. Now, of course, like with Gauss-Jacobi and linear equations, when you do solve for x1 with Gauss-Jacobi, you don't use that information until after you solve for all of the new x2, x3, etc. Gauss-Seidel says you take equation 1, solve for x1, you get that new guess for x1, and then when you come to equation 2 to solve for x2, you use that new approximation of x1 to get x2, and then etc. So this is Gauss-Seidel, where as soon as you know a value of x1, you use it then to compute x2, x3, etc. This is Gauss-Seidel, and this is not parallelizable. However, in some cases, it's more likely to be stable than Gauss-Jacobi. Basically, it's the same kind of ideas as we went through with Gauss-Jacobi, Gauss-Seidel with linear equations. Now, we can do, yeah, and then whatever methods we use in linear or one-dimensional equations we can use here, whatever ideas we used for multivariate linear equations we can use here, extrapolation, acceleration, dampening. You can also apply the Gauss-Jacobi, Gauss-Seidel ideas in a block fashion. So for example, I say if your four goods are apples and oranges and then cheddar cheese and Swiss cheese, what you should probably do is put apples and oranges in a block and the cheese is in a block, and then you have apples and oranges, you have two unknown prices and two equations, and then you fix the cheese prices when you solve there. Here you do the cheese equilibrium, holding fixed the fruit prices. The reason you want to do that is because the demand for cheddar cheese may depend a lot on the price of Swiss cheese, etc., and back in reverse, and the same between apples and oranges. So you're not going to get a nice diagonal Jacobian, but you may get what is a block diagonal Jacobian. Is that basically the Jacobian of this system is going to have a 2x2 block representing the apples and oranges, and another 2x2 block on the lower right-hand corner representing the cheese economy. So these are all basically the same ideas as we talked about with linear equations, and the convergence theory is exactly the same. Why? Well, because as you iterate, as you get close to the solution, and the system of equations is differentiable, then basically when you're close to the solution, you really just have a linear system to work with. Because if you have let's say differentiable function, and you're close to the solution, then a linear approximation is quite valid. And so basically all those ideas for linear equations translate to nonlinear equations close to the solution. So that's an option, that's possible. Now, there are some cases where you know that you have a contraction mapping. Now, what is a contraction mapping? Suppose you have a function that takes D, a subset of Rn, to Rn. And we do know that F takes that domain to a subset of that domain D, and that the Jacobian of X at every point is strictly less than 1. Then X equals F of X has a unique solution. And that you can just do this iterative scheme, xk plus 1 equals F of xk, and that will converge to that unique solution. And then here's an error bound expression. Now, the application that you're most familiar with that uses this is, of course, dynamic programming. Because after all, finite state dynamic programming is nothing but a bunch of linear equations. The value function today equals some max of some stuff over value functions tomorrow. So basically, it's a fixed point problem. Infinite horizon problem is just fixed point. And you have contraction mapping because as long as the beta, the discount factor, is less than 1. So in dynamic programming, you've seen this principle of a contraction mapping. And there are some other applications of this. One non-trivial application of the contraction mapping was, of course, Lucas's non-neutrality of money paper. But anyway, so contraction mappings are common in economics, and then you can just do an iteration. You just basically take your X, plug it into F of X, that's your next guess, and then you keep going, and that will converge. However, convergence is linear. Again, it's at the error, the distance from the k plus 1 guess to the truth is bounded above by something, which presumably is less than 1, hopefully, times the distance that the old guess was from the truth. So this is, and there again, basically the thing is that if the spectral condition number of this is less than 1, then boom, you're in. So this comes up in some cases as that can be, as a method that can be used. Now, by the way, again, I want to repeat what I said about how do you know when to stop. See, here the problem is even worse. See, with linear equations, you have a matrix A. And when to stop is just a matter of, has to do with the eigenvalues of this matrix. And the function, let's say you're trying to solve AX equals B, well, that's a linear function, which means that the function part AX has a constant, has the same structure everywhere in the domain of X. Now the problem is that when you have a nonlinear system of equations, we do know that the local behavior is related to the Jacobian, but that Jacobian is changing as you move through space. So you don't have the constancy of or the stability of a nonlinear, of a linear problem. So, but again, the same kinds of ideas can be used to decide when to stop. So you want to keep going. You want to keep going until you're pretty sure that the distance between your current guess and the solution is bounded above by some epsilon. So as we did with linear equations, we continue until the change between in the iterates is bounded above by 1 minus beta times epsilon, where beta is something like a contraction factor. And then beta is the spectral rate, or beta is the spectral radius of the Jacobian. Now, where do you get that? Well, you can't get that. You can't get the spectral radius of the Jacobian at the solution until you get to the solution. This is not, in the linear equation, this is spectral radius of A. And you have A, but you don't have this. So now sometimes we know beta as with when you have contraction mappings, but that's unusual. So again, as I said, outlined for series in general, or sequences in general, what you should do is estimate your, okay, so this is slightly different than what I had described earlier about convergence test, but you can use those ideas also, is you take the distance between the last two iterates and then divide by the distance between the most recent iterate and the one that was L iterates before, and take the 1 over L root of that ratio, and that should roughly be equal to, if you're close, this will be a good approximation to the spectral radius. So again, you keep, as you proceed, you keep updating this beta hat estimate of essentially of the spectral radius, and then you keep going until the change in the iterates is less than 1 minus beta hat times epsilon, which is your target accuracy, and you keep updating your beta hat estimate. So again, you need to use, you need to approximate, you need to have an estimate of the rate of convergence, which is essentially the spectral radius of the Jacobian at the solution, and you can't find that out directly, so you just look at, remember, the assumption here is that your sequence is converging to the solution. And you know if that's true, given that it's a simple iteration, you know that the rate of convergence is linear, which means that there is such a beta that represents the rate of convergence. And so then you estimate the beta with this kind of rule or something similar. Now, by the way, does this matter? There's a paper that Uli Dorzelski and I wrote many years ago, and it got published some years ago. I believe it got published in Quantitative Economics. But it was, so it's Dorzelski and Judd. And I think until recently, that was a unique, there was a unique Dorzelski-Judd paper. And so we showed in the context of solving out dynamic games of the Pockets-McGuire fashion that the usual stopping rule that people were using in that literature was grossly inadequate for assuring accuracy. And then we showed that this kind of approximation of the beta did help you and give you an assuredly, much more assured accuracy. So this is something that, well, was used in that one paper, should be used more generally. Now, of course, the gold standard, as always, is Newton's method for multivariate equations. So basically the idea is the same as with Newton's method for one dimension. You take, if you're at some xk point, that's your most recent guess, you replace the function f with a linear approximation at xk, and then that linear function has a zero, has a solution, and so that's then your next guess. Now, okay, more formally, if you are currently at a point xk, then the locally linear approximation is expressed in this manner. You're based at f of xk, that's the first term here, and then you have this, if you're at some x, then the second term is some arbitrary x minus your base point xk, multiplied by, this is a vector, and then that's pre-multiplied by a matrix equal to the Jacobian at xk. So that is the linear approximation of the function f at xk. Now, its zero then is written as this: xk plus 1 equals xk minus the inverse of the Jacobian times f. Now, one thing you notice that, first of all, this inverse had better exist. So this Jacobian had better be an invertible matrix. If not, you're in bad trouble. Now, even if it is invertible in a formal mathematical sense, that doesn't mean that you're out of trouble, because it could be the case that this Jacobian matrix is highly ill-conditioned. And then that means that anything that attempts to compute the inverse is going to be full of errors. So you need to, again, choose units and choose the definition of equations such that the Jacobian of the system is well behaved, and the Jacobian is not singular, but also not even close to being singular. So again, you have to watch out for these kinds of problems. Now, and again, what happens here, Newton's method, well, of course, you've got your quadratic convergence, as always. Now, there are problems with this. The Jacobian may be expensive to compute, may not converge, and those are the two issues. Those are the two problems. The Jacobian is expensive and it may not converge. Now, we call it, okay, numerical analysts call it Newton's method. Now, statisticians tend to call this Newton-Raphson method. It's the same method. It's just that Raphson did contribute to the evolution of these ideas, and Raphson was a statistician, so statisticians include him. Now, there's an article in Siam many years ago that basically said, look, if you actually want to trace out the intellectual history, it probably really should be called Newton-Raphson-Fourier-Simpson method. By the way, the Newton's version of Newton's method would be unrecognizable today if you tried to read it. But he had the key idea, and then it was developed into the form we see now. But Newton and Newton-Raphson are the same. It's just a sociological difference in behavior. Okay, there are solutions. One is to approximate the Jacobian. Just as with optimization, we approximated the Hessian. And then there's something we're going to call Broyden update, which will improve the likelihood of convergence. Now, there are some methods called homotopy methods for which there do exist convergence, almost everywhere, convergence proofs. I'm not going to talk about them today. Later on this semester, Carl Schmetters is going to talk about homotopy methods. And also, Philip will be showing you some software that he's developed along using homotopy methods and some other software tools. So I leave that for them. Carl's PhD thesis was on applying or developing a homotopy method for a general equilibrium with incomplete asset markets. And his advisor was Curtis Eve, so he's an expert on the homotopy side of the literature. And so I'll let him speak to you about that later. Now, let's see, however, examples of where we have these problems. Now, okay. Now, here's another one of those CDFs. Now, here we're trying to find the intersection of this curve, which is a sine wave, and the blue curve, which is a circle. So we're trying to find the solution. Now, so we move this point around, and this point tells us the initial guess. And so as you might expect, if you start close to this solution as initial guess, you go to this solution. If you start close to this solution, then you'll go to this solution. Okay, not surprising. Now though, look at what happens. Okay, I wander around through here and notice that through this region, you always converge to this solution. However, now watch as I move from here and, oops, okay, whoa. All of a sudden we ended up at the other solution. And now, again, at the other solution. Oh, but now things look more behaved. Oh, and that's good. But now over here, well, we end up with that solution. Well, that makes sense because that's closer. But then look at this. If we start over here to the upper left, now we end up going to this solution. Now, if you look carefully at this picture graph, you'll see that in some areas, there's a lot of dots, but some areas, it's all white. The dots represent points such that if you start Newton's method there, you will converge to this point. Whereas if you start Newton's method in one of the white regions, then you will converge to that point. Now, notice that the convergence region for this point has a rather messy boundary with the regions where you converge to the other solution. Now, okay, you do have this nice boundary here, but everywhere else, it's a kind of a messy kind of boundary between what happens if you start there or start a little bit away from there. Now, so this is a very general property of solving nonlinear equations when there are multiple solutions. Newton's method is likely to send you on a wild trip. Now, by the way, some of you may have seen pictures of what we call fractals and how you get these very interesting regions of different colors, and then the boundaries between the different colors are very crazy. Well, those things are generated as iterates of Newton's method for solving nonlinear equations. Or actually, it's a univariate equation, but in complex space. So it's really two equations and two unknowns. So basically, this behavior on the part of Newton's method is the foundation for fractals. So this, and now notice that the reason I'm showing you the two-dimensional example is that in the one-dimensional example, you just have an interval, and so there's some intervals, some subintervals where it goes to one solution, some subintervals goes to another. But here, you get to see just how complex that boundary is, and this is just 2 dimensions. Now, suppose we had 3 dimensions or 4 dimensions. This just gets worse and worse and worse if you have multiple equilibria. So these are the kinds of problems we have to address. I should point out, by the way, that for those of you who do dynamic games of the style of Pockets-McGuire, where you have, each firm has a finite number of states, there often are multiple equilibria. And there's a paper by Dorzelski and Satterthwaite and I think Bisection and Krukov in Econometrica, which demonstrated that for a simple example, that multiplicity in it is very common for those kinds of games. Multiplicity is also an issue when it comes to general equilibrium. I gave the Kehoe example I gave you was an example of multiple general equilibria. There hasn't been as much systematic study of that. People proceed as if there's unique equilibrium. And I don't know, perhaps it's, my impression is that people aren't as disturbed about multiplicity in general equilibrium, perhaps because experience is that there does appear to be a unique equilibrium. I don't know, but multiplicity in dynamic games is an enormous problem. And it's there, and you really can't avoid it. Now, suppose the Jacobian is too expensive to compute. Now, just as earlier with one-dimensional case, suppose that the f prime, the derivative of f, was too costly to compute. Well, this is just, the Jacobian is just the n-dimensional generalization of the derivative. And it could be, I mean, taking derivatives of functions gives you enormously messy expressions, and taking finite difference approximations will require lots of evaluations of functions. Anyway, so this may be costly. Now, in R1, the solution we showed was the secant method. So you didn't compute any gradients or any derivatives. You just said, okay, I know where the current guess is. I know f of xk. I know what f of xk minus 1 is. I just connect those 2 dots, and then I get a secant, and I use that. Can we do this for n-dimensional space? The initial answer is no, because suppose you did know the current guess xk and the last one xk plus 1. That just gives you a one-dimensional restriction on any sort of approximation of the system. So you'd end up, you could use that as an approximation, but that's only a one-dimensional approximation, and it's not going to pin down all the elements of the Jacobian. See, now you can try to approximate the Jacobian. The Jacobian is n squared elements. And these Jacobians aren't going to be symmetric. So you have full n squared unknowns. And so you can't just like take information at 2 points and pin down all n squared unknown elements of the Jacobian. So what you do is you have to be a little more clever. So you start with some initial Jacobian guess A0, which, by the way, is the identity function is what's used. Now then, you use whatever your current guess is for the Jacobian, use that to compute the Newton step. So you say the Newton step is such that basically that a k sk plus f of xk equals 0. So this is the solution for the Newton step. Oops. And so this is your next guess, xk plus 1. Now, what you want to do is update your Jacobian approximation. Now you have new information in the sense that you now know what f is at xk plus 1. So you have n bits of information, n items of information, the components of f at xk plus 1. Now you have those n squared elements of the previous guess, ak. Now you have n new items of information from the values of f of xk, and so you want to use that to update the n squared elements of the ak. So what you do is you want, this is now the secant equation in n dimensions, that the difference between fx at a new guess and the vector at the old guess, that difference should be compatible with this new Jacobian approximation matrix multiplied times the step you took. But that only pins down n unknowns amongst these n squared unknowns in the new Jacobian approximation. But now what you do is you impose enough extra restrictions so that you do tie down the new guess. And so basically you look at directions that are orthogonal to the Newton step. So suppose you went down that Newton step, and then but you're looking at the directions q that are orthogonal to that, and you basically say that the projection of the Jacobian matrix does not change between the old guess of the Jacobian and the new guess. So you just say, okay, we do know that you had these changes in that the new Jacobian has to be like this, and so it's going to behave differently when mapped, when it hits SK, but you're saying that, well, any other direction orthogonal, we're going to assume that the new Jacobian behaves the same as the old Jacobian. Now you've pinned down, well, you've put on a lot of restrictions, and what happens is that you end up with the Broyden update. The new Jacobian is equal to the old Jacobian, and then in the denominator here is basically the L2 norm of the Newton step. So when I write these things, I'm thinking of these vectors as being column vectors. And so SK transpose times SK, that's a row or inner product between a row vector and a column. And so this is going to be a scalar. If it's in the denominator, it better be a scalar. And then you take the old guess and the y value, the value of f at the old guess, and you take this difference and then multiply that by the row vector of the Newton step, of the step you took, and that gives you a new Jacobian. So, and your yk is a change in the f value of from the old guess to the new guess. So this is your Jacobian update. Now, why am I telling you about it? Well, because it's an idea that does seem to work. There's some theory behind it. I'm not going to go into the theory, but it works in the sense of solving for the solution to the nonlinear equation. So the xk's will, under appropriate circumstances, converge to the solution for the nonlinear system of equations. Again, though, the Jacobian approximations are not going to converge to the true Jacobian at the solution. This is even more apparent here, but in both cases, what's happening is you start with some initial Jacobian, you're updating it slightly at each iteration. You really have no reason to expect that it converges to anything close to the true Jacobian. So, so you will solve the nonlinear system equations, but if you need the Jacobian at the solution, you've got to do that directly. It's nice to have a good initial guess for A0, as well as for X0. But a lot of times you're just stuck with using the identity matrix. Now, the key thing is that each iterate here is very cheap, because computing the Newton step is you take your most current Jacobian, and this is just, if you take the most current Jacobian, aka you have value of f at the most recent iterate, you just solve this linear set of equations, and you have your Newton step. You move by that, make that change, and then now all you have to do is compute the difference. You have to compute f at the new guess, well, which of course you're going to have to do for other reasons. And this yk is just the difference, the progress you've made, the vector of the differences between the old guess and the new. And then you use this, again, just all linear operations here, and to update your Jacobian. So this is much faster than a Newton's method, which would involve computing out the full Jacobian. Now, of course, the cost is that you're going to need more iterations. But this trade-off, particularly for large systems, is well worth it. That you make each iteration of the Breuer method is orders of magnitude faster than a Newton step would be, but the number of extra iterates is much less than that. So, again, the Breuer method, I mean, see, with Newton's method, both optimization and nonlinear equations, you don't need to have a really good approximation for the Hessian or the Jacobian in order to make progress. That there are these very cheap things to compute that will help you make substantial progress, whether it's trying to find the bottom of a hill or a zero of a set of functions. You can use cheap approximations to make progress, and then you just keep doing that. Now, the other problem, and one that really is much more severe, is the possibility of non-convergence. And that's why I showed you those two examples that now the first one-dimensional example showed you that if you know that the solution is within some range, Newton's method could easily kick you out of that range. Now that didn't happen with that other one that stayed within the range. But the thing is, Newton's method, uncontrolled Newton's method, can easily diverge, send you into crazy regions where your functions aren't defined, and not get where you want to go. So you have to control that instability in Newton's method. Now, in the case of unconstrained optimization, what did we do? We used the concept of search directions. So we used the Newton step as a direction to go, but then we said, okay, now how far in that direction should we go in order to minimize the function we're minimizing? Now, optimization is a cleaner problem because we know what the criterion is easy. It's to reduce f of x, the value of f, reduce it. And so basically we have a search direction, and what we need to do is just find some search direction that goes downhill. And we know that the Newton step will always go downhill. So it's a matter of how far you take the Newton step. And so that's why you then, instead of using Newton's step as a step, you use it as a definition of a ray, and then you do a one-dimensional optimization along that ray, and you know you're going to get to a lower value. So you have this criterion of going downhill, and you can always find some way to go downhill. It's a matter of going downhill fast. Now, with nonlinear equations, what you're trying to do is you have no such guide. You're trying to find an x or n n numbers in the vector x such that n equations are all equal to 0. Okay, that's what you want, but if you're at an x and you find that f of x is not 0, it's a bunch of non-zero numbers, that really doesn't tell you how far you are from having to the solution. That's not much information to go on. So what you have to do is come up with some kind of indicator telling you whether or not you're going in the right direction. Now, let's back up a bit. One could say, well, gee, why don't you have these functions, fix, and you want to set them all equal to 0. Well, gee, why don't you just square all of them? Take the sum of squares of all these equations and minimize it. Because then now, if some x star solves f of x equals 0, then it is a global solution of this minimization problem. So why don't we just send this off to some minimization problem and tell it, okay, just minimize this thing. Just keep going downhill, downhill, downhill. No. And then use optimization procedures. Now, there are two problems with that. One is, this is basically nonlinearly squares. And when you square this and add up the squares, you may have a function that has a lot of values. And this is a case where all you care about is the global minimum, where basically each of these fi functions is 0. That's all you care about, is the global minimum. But if you create this objective function, SSRX, you may have created a function that has lots of hills and valleys, and so you could get stuck at a local min and have no idea how to get out of that. So directly to do that is not a good idea. The other problem is, what is the Hessian of this? The Hessian of this is going to be ill-conditioned. Why? Because as we saw, by the way, with some least squares thing we did, the Hessian is roughly equal to the square of is well approximated by the transpose of Jacobian multiplied by the Jacobian. It's basically kind of a square of the Jacobian, which means that the condition number of the Hessian at the solution is going to be twice the condition number of the Jacobian at the solution. Now, so even if you have a system that looks nice and the Jacobian matrix has condition number 6 or 7 each time, then if you take this procedure, then at the solution, the Hessian is going to have at the condition number is going to have a condition number like 12 or 14, which is disastrous. The computer will not give you a good solution. So you cannot take this idea directly. However, what Powell decided to do is to use this criterion as a check. So in the Powell hybrid method, he says, okay, we do Newton, but then I kind of want to check to see what's happening with this SSR criterion. So now, if I take a Newton step and SSR, the sum of squares, increases a lot, well, that kind of tells me I probably went too far in the wrong direction. It's not a good idea. So then, according to Powell hybrid, if you have a Newton step, which substantially increases SSR, you then say, well, gee, I don't have a good idea. Newton's method is not working. So then what I'm going to do is to switch to nonlinear least squares. So I will switch to nonlinear least squares for a while. See, away from the solution, the Hessian of this may be well conditioned. And so maybe it can send you downhill. So you switch to least squares. And then when you have driven this SSR number below what it was before, well, then you say, well, now I'm kind of back in the good territory. And so then I switch back to Newton's method. So that was Powell hybrid method, is that you do Newton's method, but you keep checking this SSR criterion. And if it's going the wrong direction, you then switch to the minimization problem and track some x's, which are hopefully getting closer and closer to some solution. And then when you sort of beat down the SSR criterion, then you switch back to Newton's method. Because Newton's method, you see, the SSR criterion will not take you to a solution. If as it goes close to the solution, there's going to be ill conditioning problems. But it will help you get in the general neighborhood of a solution. And then if you want to get into the solution, you then switch to Newton. So this is very successful. Now, the Powell hybrid method was introduced in the early 70s. And actually, my impression is that prior to that, Newton's method was considered just crazy idea, it doesn't work. But that Powell's hybrid method really stabilized it, and then it became much more widely used. That's my impression. I should ask my buddies to see what the nature of that history is. So, so again, this is, by the way, this is an example of what we call hybrid. Okay, you want to do Newton's method because if you get it close to if you're close to a solution, it'll go zoom right down there quadratically. But when you're not close to a solution, you can try Newton's method, but maybe it's going to be okay, maybe not. If it's going bad, then you switch to nonlinearly squared to push down this sum of squared residual criterion, and then go back to Newton when you think you've gotten closer to the solution. It's a hybrid method. And with this case, you see, Newton's method will work if you're close to the solution, maybe not globally. SSR will globally help you move towards a solution, but it's not going to get you to the solution because of the ill conditioning of the Hessian if you get close to the solution. It's a hybrid method. And this, again, is just an example of why I emphasize there are multiple ways of solving any of your problems. Try them to find out which ones to use, and or try combinations, because different methods have different success rates in different circumstances. Okay. Now, software-wise, now there is a nonlinear equation solver in MATLAB, FSolve. My impression is that it's of a Powell hybrid method. I haven't closely looked at the documentation, but let's say many years ago, FSolve only did the sum of squared residuals minimization. And so when I saw that, I said, oh, another example of MATLAB being lousy. But then they now have improved things dramatically. I think it was many years ago, I made comments to computational mathematicians about how bad the optimization and nonlinear equation stuff was in MATLAB. And then somebody said that he mentioned that to some MATLAB people, and they said, well, give us a break. They don't let us spend much time on those nonlinear equations and nonlinear optimization stuff. So, but now they have invested significantly. And so MATLAB's nonlinear optimizers and nonlinear equations are competitive, or using good algorithms. Now, oh, there's this guy, Kelly, that has some MATLAB programs that does this. I'll be sure. My Zurich buddies will make sure I post them. Now, here's the other fact, though. You're not going to find, oh, now, by the way, the gold standard in solving nonlinear equations is a package called PATH, P-A-T-H. The thing about PATH, though, however, is that it really is designed to solve things that we call nonlinear complementarity problems, which are generalizations of equations. Now, so for a lot of the things that you do, my recommendation is to use constrained optimization software to solve nonlinear equations. And then Thursday, we'll talk about constrained optimization, but the idea basically is you put the equations in the constraints, and then you tell the computer, well, minimize 1 subject to these constraints. Well, the objective is a constant, and so basically all that's going to happen is that the solver is just going to try to solve the nonlinear equations in the constraints. And so basically the best Newton-style code for doing nonlinear equations is buried inside of constrained optimization packages. And then I will also show you some reasons why that has a lot of advantages over just a nonlinear equation solver. This is this is why I'm telling you to hold off on trying to solve non-trivial system equations, because the way to solve them is to really treat them as constrained optimization problems. Now, a little historical note on general equilibrium. Those of you familiar with, those of you Americans familiar with general equilibrium might have heard about Scarf's algorithm. And Herb Scarf did come up with an algorithm that was surely convergent for solving general equilibrium. Now, I don't think it's used at all anymore because it is slow. The primary contribution of Scarf's work was to lay the problem out in a manner which laid out some ideas which then were followed up on by OR or by computational math people and led to some of the homotopy methods. So it's, when you look at Scarf's method, it's very much like a homotopy method, but then if you understand this homotopy method, then that helps you develop things further. So Scarf, I think his students, Chauvin and Wall in particular, used Scarf's method when they wrote their work, computational work in the 1970s. But I don't think it was ever widely used. Now, I say this is what you Americans might have seen. Now, by the way, in Europe, and so some Americans will say that Scarf was the father of applied general equilibrium, computational general equilibrium field. Now, Europeans will disagree with that because they will point to the work of Johansen, I forget the first name, who published his PhD thesis in 1960, and that was basically published as a book. I have a copy, and it basically lays out a method to solve the general equilibrium of the Norwegian economy. And it was his ideas, his approaches, which then were used in the applied general equilibrium field, and even to this day is commonly used. Europeans regard him as the father of computational general equilibrium. Why this gap? Why this difference? Well, one reason is that Johansen was a member of the Norwegian Communist Party, and that was not a good idea in the 50s or 60s if you wanted to travel to the US, so he wasn't able to travel to the US, so his ideas weren't really disseminated much in the US, and then he died at a young age in the 70s. So that's why, one explanation for why his ideas just never got over here on this side of the Atlantic. So now, the fact is now that when people solve general equilibrium problems, the path solver is probably the best that is available. But I'm surprised when I talk to applied GE people and they are still using approaches that go back to Johansson stuff, and it's kind of also Gauss-Jacobi, Gauss-Seidel methods anyway. So that's my comment on applied general equilibrium. Now, by the way, path is one of those things. Oh, by the way, path is not in the public domain. I know Todd Munson would like to put it in the public domain, but there's a piece of it which somebody owns copyright or patent on. But however, it is easily available through Ample and GAMS. If you really wanted to use it from MATLAB or even Fortran or some things, then you tell me, and I think Todd is willing to help out and distribute it that way. But Path is an example of a software package that is so much easier to access and use through the Ample or GAMS modeling languages. That's my comments on the software side of this. Now, any question? Okay, I think what seems to work here is I say, this is the official end of the lecture.